In today's lesson, we are going to look at some problem solving with combinations. So we're going to look at some kind of little tips and tricks that we can use to help us with some of these questions, to help it make it easier to solve some of these rather than going through and looking at all the scenarios. So again, just some general formulas to help us again, but not something that you need to rely on. It's just some things to help make it a little bit easier. So we're going to look at an example when we're dealing with distinct or all different items. So how many selections are possible from a bag containing one red, one blue, one green, one yellow, and one orange marble? And we're told that we must choose at least one. So again, some key information: one red, one blue, one green, one yellow, and one orange. And we must choose at least one. So that's a key thing there. So looking at this scenario, I have 5 different objects. And of these 5 different objects, I must choose at least one. So there's a bunch of different cases here. The first case would be 5 choose 1. I'm choosing one object. The next case is 5 choose 2. I'm choosing 2 objects. Now how would these two relate together? Well, in this case, I would have to add these two together. And the reason I am adding them is because OR is implied. And what we mean here is that we are pulling one marble or 2, because again the question said at least one. So we could have a scenario where we pull one marble or 2 or 3 and so on. So if we continue this, we're going to add 5 choose 3 plus 5 choose 4 plus 5 choose 5 for all the different scenarios, choosing 1, 2, 3, 4, or 5 marbles, because we're choosing at least one. And when we go through and solve this, we should get that there are 31 ways. So out of a bag of 5 marbles, there are 31 ways to choose at least one. Now, this could get long in terms of calculations. It could get very tedious if we have more and more distinct items. So is there an easier way to solve this? And in this case, there is. So in general, when we're dealing with all different items, the total number of combinations containing at least one item chosen from a group of n distinct objects, so they're all different, is 2 to the power of n minus 1. So the 2 represents the fact that each element or each object, call it object, each object has 2 ways of being selected or chosen. And those 2 ways are either yes, it's selected, or no, it's not selected. The n represents the number of total objects, and the minus 1 represents what we call the null set, where the null set is basically when no objects are selected. So you could also argue then that if this is the case, for when you're choosing at least one item, all possible combinations from a group of distinct objects is going to be 2 to the power of n. But if we're choosing at least one, we have to subtract that null set, or that set where none of the objects are selected. So for at least one, it's 2 to the power of n minus 1. If we go back up to that last example, we can see that this formula does work. 2 to the power of n minus 1 becomes 2 to the power of 5 minus 1, which works out to 31 as well. So even when we go back to the previous example, instead of going through and doing every combination, we could use this general formula. Again, this only works if we're choosing or we're told that we're choosing at least one item. This also works when we're dealing with some identical items. So in this case, we're going to be dealing with if a set contains A, B, and C indistinguishable or identical objects, and you must select some or at least one. So if we're dealing with multiple objects that are the same, then this kind of changes it. It becomes the number of objects plus 1 times the number of the second object plus 2, and so on. And then we still subtract 1 for that null set, or that set where we don't have any. And the idea of this is the same as the previous one. Rather than it being 2, it's either selected or it's not. Here, depending on how many objects we have, that's going to change how many possible selections we have for each one. And then we still add the 1 for the option where we don't select any of them. So let's look at an example. A bag of marbles contains 1 red, 3 blue, and 2 green marbles. If you pick some without looking, how many different selections could you make? So again, key things: 1 red, 3 blue, and 2 green. And we pick up some. We pick up some marbles without looking. How many different selections could you make? Well, rather than go through and look at all the different possible combinations of each individual one, or each individual marbles and looking at that, I'm going to use that formula that I just looked at. So if I'm looking at my red marbles, thinking of my general formula, if I want, let's put it just above. So we have A plus 1 times B plus 1. Change the colors. B plus 1 for blue times C plus 1 for green will equal my total number of, oh, sorry, we forgot the minus 1 for that null set, which will equal our total number. So if I look at our red, well, how many options do I have? Move this down. Another way we could think of it, well, I have 1 red, and I have the option of selecting, or one option of selecting no red. So in total, I have 2. In my formula then, this would be 1 plus 1 times, and now we're going to look at the blue marbles. So if I look at my blue marbles, what options do I have? Well, I have 3 blue, plus the option of picking no blue, which leaves me with 4. Or my formula, 3 plus 1, which gives me 4. For my green marbles, same idea. I have 2 green that I could select, and I have the option of selecting no green. So that means 3 options. Or in my formula, 2 plus 1. I still subtract 1 in either case for that null set, that set where I don't have any. And when I do that, I should get 23 ways. So the top one, we're just dealing with the formula, and then we're kind of breaking it down into each part to see where those numbers actually come from. And in the end, we get 23 ways. So again, a lot easier than going through for the red, 2 choose 0 and times 2 choose 1, or looking at all the different scenarios of either 1 red or no red, and so on and so on and so on. So a lot easier to work our way through it this way than go through and look at the combinations of each individual item. Moving on to the next part. So again, now we're just going to look at some different scenarios, different types of questions, and kind of problem solve through it so that when you come across these different types of combination questions, you are comfortable working through it. So a director of a short film has 5 rock, 2 blues, and 3 jazz pieces he can select from. How many ways can the director choose 3 pieces if he wants to include jazz? So in this case, there's going to be 2 ways that we can do this. So we're going to look at the direct way first, and then we'll look at the indirect way. So if he wants to include jazz, in this case we have case 1, where he's going to choose 1 jazz piece. So in this case, he has, let me go back and actually highlight, there's 5 rock, 2 blues, and 3 jazz, and he's choosing 3 pieces. So in case 1, for jazz, 1 jazz, we have 3 jazz choosing 1, and for all our other options, we have 7 options choosing 2 of them, because again, we're looking for 3 pieces. So 3 choose 1 times 7 choose 2 equals 63. For case number 2, we're looking at 2 jazz pieces. So this kind of changes. Now it's 3 choose 2 times 7 choose 1, which equals 21 cases. Or combinations, or ways. Case 3, we're looking at 3 jazz pieces, so all the pieces that he's choosing are jazz. We have 3 choose 3 times 7 choose 0, which works out to 1. Because it's case 1 or case 2 or case 3, we're going to add all of these up, because again, or implies that we add them, and we get 85 ways. So that's the direct way. So again, going through and selecting all the different cases and adding them up. If we look at the indirect way, again, we want to find the total number of ways we can select. And we're going to subtract the opposite or the impossible case of what we're looking for. In this case, if we want to include some jazz, the impossible case is choosing no jazz. And when we subtract that from the total numbers of ways, that will leave us with at least 1 jazz. So how many total number of ways are there? Well, there are in total 10 pieces, and I'm choosing 3 of them. So there are 10 choose 3 total ways, minus 7 choose 3 times 3 choose, actually let me keep it in the same format as the last one. So 3 choose 0 for no jazz times 7 choose 3 for all the other options. And this equals, again, 85 ways. So again, just recognizing this piece here is referring to no jazz. So again, just different ways that we can deal with the same question. Again, depending on what method you prefer, it might be easier for you. You can see definitely there's one that's less work, but again, it depends on how you prefer to think about it when you're working through these questions. So we're going to move on to example 4. However, before we do that, today's code word is phone. Again, today's code word is phone. So in example 4, Lindsay, Megan, and their 4 friends want to join the cheer squad. If the group only has 3 members, how many ways can the 3-member squad be formed? So we're just looking, again, we have Lindsay, Megan, and their 4 friends. And the question is asking us, how many ways can a 3-member squad be formed? So we have 6 total options, or individuals. We're choosing 3 of them. In this case, 6 choose 3 equals 20 ways. So there are 20 ways a 3-member squad can be formed. How many ways, or how many of these squads contain Lindsay? So again, there are 2 ways that we could deal with this. One, if I do the direct way. So how many contain Lindsay? Well, I have to look at one possible scenario. So one, choose one. So it has to include Lindsay. So there's only one Lindsay, and we're choosing her. And we're going to multiply that by 5, choose 2 for the other individuals where there's no Lindsay. So 1, choose 1 times 5, choose 2 equals 10 ways. The indirect way looks at the total number of ways minus how many ways with no Lindsay. So total number of ways, we've already found that. 6, choose 3 minus how many ways with no Lindsay. Well, in this case, we have one Lindsay and we're not choosing her, multiplied by 5 individuals choosing 3 of them, which still works out to 10 ways. So again, regardless of how you think of it, you should still get to the same answer in the end. How many of these scenarios or groups of 3 do not contain Lindsay? Or sorry, not Lindsay, Megan. So now we're just switching it up, looking for a different individual. But the idea is still the same. 5, choose 3. For no Megan, times 1, choose 0. So if we're looking for Megan, there's one of her, but we're not choosing them, which equals 10. Or again, you could do the indirect way, 6, choose 3 for total number of ways, minus including Megan. So here we have 5, choose 2 times 1, choose 1, which again works out to 10 ways. So again, 2 different ways you can look at it, whether it's direct or indirect. How many contain both Megan and Lindsay? So in this case, we have to look at 2 different parts, or kind of 2 different events. So we have Megan and Lindsay, and we have all the other individuals that are not Megan and Lindsay. So there's 2 individuals that are Megan and Lindsay. We're choosing 2 of them. Multiply by how many are not Megan and Lindsay. Well, there's then 4 individuals, and we're choosing 1 of them, which works out to 4 ways. And again, in a lot of these scenarios, say for example, looking back at C, how many ways can you not choose Megan? Well, we can just remove her from the group. So then there's only 5 options, choosing 3 of them. 1, choose 0 is still 1. Same with down here at the bottom. If it has to include Megan and Lindsay, that means we only have 1 position left. 4 possible people, so 4, choose 1. Right? The 2, choose 2 works out to 1 as well. But sometimes it's helpful to think about both parts or both events of the scenario as you work through it. Example 5, now this is going to get a little bit tricky because now we're going to throw in permutations and combinations together. So in example A, how many 5-letter codes can be formed from 2 different vowels and 3 different consonants? So this is where it's tricky because 5-letter codes, this is a permutation, because this is ordered. Two different vowels and 3 different consonants, these are both no order. So it's combinations. because there's no order to which vowels I choose. Same with the 3 different consonants. So this is 2 parts, one with permutations, one with combinations. So in this case, let's say, let's include for vowels A, E, I, O, U, and Y, just for sake of argument. So in this case, we have to look at our combinations first. So how many different ways can we come up with 2 vowels? Well, we have 6 choosing 2 for our vowels. Because we have 6 vowels, we're choosing 2 of them. We're going to multiply that by how many consonants do we have? Well, 20 choose 3. 20 consonants choosing 3 of them. So that's how many different combinations of letters that I could have for my code. But now I have to multiply it by 5 factorial for the order. Actually, so let me go back and color code this. So the red is for my combinations, the blue is for my permutations. So 6 choose 2 times 20 choose 3 to give us the different combinations of letters that we have, times 5 factorial for the different orders that they could be in. So in total, I get 2,052,000 codes. So again, this is an example where we have both combinations and permutations together. For B, how many of these combinations include the letter C? So we're taking that same idea, but now we're throwing in the little curveball that we have to include the letter C. So let's go through it again. Let's look at our consonant or our vowels. Well, we still have 6 vowels and we're choosing 2 of them. We're going to multiply that by, I need to include the letter C. So there's 1 C, I'm choosing 1 of them. And then I'm multiplying that by the rest of my consonants. So in this case, there are 19 other consonants and I'm choosing 2 of them because again, I need a total of 3. And then for the order, I'm multiplying by 5 factorial. So, how many combinations include the letter C? Well, 6 choose 2 for vowels times 1 choose 1 for including the letter C times 19 choose 2 for the remaining consonants times 5 factorial for the order works out to 307,800 codes. So 307,800 codes. So again, looking through this lesson, again, this is just showing you different types of scenarios that you could come up with. Again, focusing on the indirect and the direct, giving you a shortcut if you have to figure out at least one or some, right? So rather than go through and add up all the cases, but again, keep in mind it's different for when we have all distinct items and we have some identical items. But again, focusing on the fact that those require, it's all items are being picked or at least one all the way up to all, right? So for some of the questions that we looked at, say for this one where we're choosing only 3, so at least 1 jazz, at least 2, so at least 1, but up to 3. So this one's going to be a little different because we're not including this for all pieces type of thing. Right, we're being a little bit more specific here. If I just want to look for a total number of combinations, then I could use those formulas. Again, indirect and direct. And then lastly, just showing how we can have questions where we combine combinations and permutations together. And again, just understanding that that can happen. So again, if you have to look back at some of the previous lessons, looking back at permutations, looking back at combinations to kind of refresh that, please make sure you do so.